On January 8, 1998, at a meeting of the American Astronomical Society in Washington, D.C., Saul Perlmutter of the Supernova Cosmology Project at Berkeley presented an impossible result. The expansion of the universe was not slowing down, it was speeding up. Within weeks, the rival DESI supernova search team, led by Brian Schmidt and Adam Rees, confirmed it from their own independent data. Something was pushing the cosmos apart. Something that did not interact with light. Something that made up the majority of everything that exists. They had no name for it. Today, we call it dark energy, and nearly 30 years later, we still do not know what it is. In this video, we are counting down 10 of the deepest open questions about dark energy. Some have been studied by the Planck satellite, some by the Dark Energy Survey in Chile, some by the new DESI collaboration in Arizona. Some only exist as equations on a chalkboard, waiting for an instrument that has not yet been built. We will start at number 10 and work down to a single problem so severe that physicists call it the worst prediction in the history of science. The number is wrong by a factor of 10 to the 120th power. Stay with me. Number 10. The discovery itself. Through the 1990s, two teams of astronomers were measuring distant Type 1a supernovae, exploding white dwarf stars that, because they always detonate at the same intrinsic brightness, can be used as cosmic distance markers. The expectation was simple. The expansion of the universe, set in motion by the Big Bang, should be slowing under the gravity of all the matter inside it. Instead, the supernovae were dimmer than predicted, fainter, farther away than they should have been. The teams checked their work for years. The DESI team published its definitive paper in the Astronomical Journal in 1998. The Supernova Cosmology Project followed in the Astrophysical Journal in 1999. The conclusion was the same. The expansion is accelerating. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for the discovery. But the prize did not solve the problem. It only confirmed that the problem was real. Number 9. The cosmological constant problem. Albert Einstein introduced a term into his field equations in 1917, a constant labeled lambda to allow for a static universe. He later called it his greatest blunder. When the supernova results came back in 1998, lambda returned. It is the simplest mathematical description of dark energy, a constant energy density built into the fabric of space itself. The problem is the value. When physicists try to calculate what the energy density of empty space should be, using quantum field theory, the answer comes out roughly 10 to the 120th power times larger than what we actually measure. That is a 1 followed by 120 zeros. Steven Weinberg laid out the full scope of this discrepancy in a 1989 paper in Reviews of Modern Physics, and it has come to be called the worst theoretical prediction in the history of physics. The disagreement has not narrowed since. Number 8. The Hubble tension. The expansion rate of the universe is called the Hubble constant. It can be measured two ways. The first uses the cosmic microwave background, the afterglow of the Big Bang mapped in detail by the Planck satellite, with results published by the European Space Agency in 2018. The second uses nearby supernovae and Cepheid variable stars, refined by Adam Rees and the SH0E's team using the Hubble Space Telescope, and more recently, the James Webb. Both methods are precise. Both are well tested. They disagree. The early universe value sits near 67 kilometers per second per megaparsec. The local universe value sits near 73. The discrepancy now exceeds 5 sigma, a less than 1 in 3.5 million chance of being a statistical fluke. James Webb data released in 2024 ruled out crowding and dust as the explanation. Either dark energy is doing something different than we assume, or one of these measurements is wrong. Nobody knows which. Number 7. Is dark energy actually constant? The simplest model assumes its strength has been the same for the entire history of the universe. But in April 2024, the Dark Energy Spectroscopic Instrument Collaboration, operating at Kitt Peak National Observatory in Arizona, released its first major cosmological results. Drawing on the positions of millions of galaxies and quasars, the DESI team reported tentative evidence at the level of 3 to 4 standard deviations, depending on which datasets were combined, that dark energy may not be constant after all. Its strength may have weakened over the last few billion years. In March 2025, DESI's second data release strengthened the signal to roughly 4.2 sigma. The result is not yet definitive. But if it holds, it would mean the cosmological constant is not the right description of nature. It would mean dark energy is dynamic. Something is changing inside the vacuum, and we do not know why. Number 6. Quintessence. If dark energy is not a constant, what is it? One leading proposal, developed in the late 1990s by Robert Caldwell, Rahul Dave, and Paul Steinhardt at the University of Pennsylvania, and published in Physical Review Letters in 1998, is called quintessence, a name borrowed from Aristotle's fifth element. The idea is that dark energy is a dynamical scalar field, slowly rolling down a potential, like a marble rolling along a very gentle slope. Its strength changes over cosmic time. The model is mathematically elegant. It is consistent with general relativity, and it makes specific, testable predictions about how the expansion rate should evolve. So far, no observation has either confirmed or ruled out quintessence. The DESI results are the closest hint. The marble may be rolling. We do not yet have the precision to see it. Number 5. Phantom energy. There is a more violent possibility. If dark energy is not constant, and if it is not slowly weakening, if instead it is slowly strengthening, the universe is heading toward a catastrophe. Robert Caldwell, Mark Kamienkowski, and Nevin Weinberg, in a 2003 paper in Physical Review Letters, called this scenario phantom energy. As the energy density rises, gravity loses ground. First, distant galaxy clusters are pulled out of reach. Then individual galaxies. Then solar systems. Then planets, then atoms themselves. The model gives a name to this final moment, the Big Rip. Caldwell and his collaborators worked out the consequences for one specific value of the dark energy equation of state, W equals -1.5, and calculated that under that assumption, the rip would arrive about 22 billion years from now. Other values give different timelines. There is currently no observation that confirms phantom energy. There is also no observation that rules it out. Number 4. The coincidence problem. The universe is roughly 13.8 billion years old. For most of that history, matter-dominated galaxies formed, stars ignited, gravity ruled. Only in the last few billion years has dark energy taken over. We happen to be alive at the precise moment when matter density and dark energy density are comparable in magnitude. Slightly earlier in cosmic history, dark energy was negligible. Slightly later, matter will be diluted into irrelevance. The window of equality is narrow, and we are, somehow, inside it. Cosmologists call this the coincidence problem. There is no accepted solution. Some appeal to the anthropic principle, only a universe that allows galaxies to form long enough for observers to evolve will ever be observed. Others argue this just means the cosmological constant is wrong, and that a dynamical model like quintessence would naturally produce the apparent coincidence. The debate is unresolved. Number 3. The end of observable cosmology. Here is a thought that has not received enough attention. If dark energy continues to accelerate the expansion of space, then over the next few trillion years, every galaxy outside our local group will be carried beyond the cosmic horizon. Their light will redshift into invisibility. Lawrence Krauss and Robert Schurer, in a 2007 paper in General Relativity and Gravitation, made this argument explicitly. Future astronomers, no matter how advanced their instruments, will see only the Milky Way and Andromeda, by then merged into a single galaxy. They will see no other stars. They will have no evidence that the Big Bang ever happened. They will have no way to discover dark energy. Cosmology as a science will end, not because civilization fails, because the evidence will have moved beyond reach. We are living in a brief window where the universe is still readable. Number 2. What if dark energy does not exist at all? A serious minority of cosmologists argue that the acceleration of cosmic expansion is not caused by a mysterious substance, but by a flaw in our theory of gravity itself. Einstein's general relativity, written in 1915, has passed every test ever applied to it on solar system scales. But on cosmic scales, billions of light years across, it has never been independently verified. Modified gravity theories, sometimes called F(r) models, propose that gravity behaves differently at the largest distances. No invisible energy, just different equations. The European Space Agency's Euclid mission, launched in July 2023 and now mapping the geometry of nearly 2 billion galaxies, was built in part to distinguish between dark energy and modified gravity. Its first cosmological results are expected in October 2026. If general relativity itself is incomplete, then dark energy is not a discovery. It is a misinterpretation. Number 1. The vacuum itself. Here is the deepest version of the problem. Quantum field theory tells us that empty space is not empty. Particles flicker into existence and annihilate. Fields fluctuate. The vacuum has energy. When physicists try to calculate that energy, the result is enormous. So enormous that, if it were correct, the universe would have torn itself apart in the first fraction of a second after the Big Bang. The actual measured value of dark energy is roughly 10 to the negative 120th of the predicted value. Steven Weinberg, in his 1989 paper in Reviews of Modern Physics, framed this as the central crisis of theoretical physics. Some unknown mechanism must be canceling almost all of the vacuum energy, but not quite all. The remainder is what we observe. We do not know what survives. We do not know why. The largest constituent of the universe is, at the deepest level, the thing we understand least. Nearly 30 years after the supernova surprise, dark energy remains the largest single thing in the universe, and the least understood. We have measured it. We have mapped it. We have built satellites and ground-based instruments costing billions of dollars to study it. We have not explained it. The cosmological constant problem is unsolved. The Hubble tension is unsolved. The coincidence problem is unsolved. Quintessence and phantom energy and modified gravity remain open possibilities. And one day, if the acceleration continues, the evidence itself will fade beyond the cosmic horizon. The universe is telling us something. We are not yet equipped to hear it. If you want to keep exploring the edge of what we know, subscribe. We are only just beginning.